Welcome to Ask and Learn.
So we have a capacitor with plates like this, and we're going to stick a piece of metal in between. So this goes in X. I mean, the whole distance is L, which means that this portion is L minus X. And we know it's separated by D. And so we want to find the total energy stored in this capacitor. So that's going to be 1/2 CV squared. And I don't want to deal with the voltage, so I'll say this is Q over C, which gives us 1/2 Q squared over C. So now we need the charge and the capacitance. Well, the capacitance is A times epsilon naught over D. And the area we want, well, the capacitor is going to be whatever portion we're not having the metal in between, because the metal is going to make it not a capacitor anymore. So we want this area that's left. So we know in terms of the depth, or the length, I guess, that's just L. So epsilon naught L, and then the other dimension is L minus X divided by D. So that's the capacitance. Now the charge, Q squared over, now the charge is going to be some fraction of Q0. And so we can take the ratio of the lengths to figure out the charge because it's still evenly distributed. So this is going to be Q0 times whatever fraction is left, so L minus X divided by the entire length, and that whole thing is squared. And now let's square this out, so we get Q0 squared, L minus X squared, divided by L squared. This is 2 epsilon naught L minus X, and the D's in the denominator, so I can, I'll bring that up to the numerator like this. So now one of the L minus X's cancels. This L squared comes down to the denominator, so we get Q squared, Q0 squared, and L minus X times D, and then divided by 2 epsilon naught, and then we have an L and an L squared, so that's L cubed. And now to figure out the force, well, it's going to be in the X direction, so I'll say this is positive X. And we'll take minus du dx, and it's in the X direction, so an I hat vector, so this is a vector quantity. This comes out to minus d by dx times Q0 squared L minus X d over 2 epsilon naught L cubed. Now if we take the derivative of this, it only depends on this term here, which goes to minus 1. So this becomes Q0 squared times d over 2 epsilon naught L cubed I hat. And now we want the stress, which is the force per unit area. So, well, we're told the area is L times D, so that's just force over area. It's going to be Q0 squared D over 2 epsilon naught L cubed divided by LD. So the D cancels. And again, this L cubed is in the denominator, so we get Q0 squared over 2 epsilon naught L to the fourth. Next, we want to find the energy density, which is given as mu sub E, and that's 1/2 epsilon naught times the field squared. And the field for plates of charge is sigma over epsilon naught. This becomes 1 over 2 epsilon naught sigma squared. And sigma is just charge over area. And we know the charge is what we determined in the first part when we were doing the energy stored. So that's Q0 times the fraction of the capacitor that's still left, so L minus X over L. This is squared and then divided by L, nope, not that area, L times L minus X, the area of the plate, squared. So this is Q0 squared, L minus X squared over L squared, and the denominator of 2 epsilon naught L squared L minus X squared. So these cancel, and this comes in the denominator. We get Q0 squared over 2 epsilon naught L to the fourth. Now this might look familiar. The energy density is exactly the same thing we got up here for the force per unit area or the stress. So they're exactly the same.